Hi guys, can you hear me okay?
Yeah, sounds good.
Let me see. Hey guys, can you hear me?
Yeah, sounds good.
Okay, great. Thanks. I just had you guys off. Thank you. Oops, no. Hey guys, what do you guys know how many weeks we have left to the
We have finals on the 15th.
I'm sorry?
Finals week starts on the 15th.
So we got 3 weeks left, is that right? No. Yikes. I better check this out. Finals week starts on May 15th.
I think that's what I saw when I searched it up this morning.
It could be good, and that's good and bad, I guess, huh? Yikes. Yikes. So how many more weeks we got left? We don't have too much time. So, really? Wow. So we only have 2 weeks left? Kind of? 3 weeks? Guess I'll have to check it out. For some reason, I thought our semester is going to go to June, but oh well. Okay, I'll check it out, guys. So we had a couple of yeah. So Armand, you're saying we have 2 weeks left? Yeah. Okay. Okay. Well, good. I'm ready for the summer. All right. Okay, guys. So let's see. Where are we? I had last week. It was all recorded, so I wanted to see if anybody had any questions, and I'm just going to do like a super quick review and move on. Any questions from last week? The sections were about input and output impedance, and we started talking about biasing. Anybody's got any questions? No? No questions? Okay, guys, so let's see. Let me just do a quick review. So, really, I think the beginning part of this chapter is about kind of realities of life that are affecting our basic design of bipolar circuits. And, so one of them is, the fact that whatever's driving our bipolar amplifier isn't perfect. It has a certain series resistance. So if our bipolar amplifier has an input resistance, so if I'm just going to draw it as the amplifiers are usually drawn as triangles. So whatever source we have, whether it's a microphone, it could be really anything. It has a certain resistance associated with it. And, if the amplifier, which it always does, has an input resistance, then this has a tendency to attenuate the input signal from the source into the amplifier input. So basically, it's usually preferred to have, I'm sorry, guys, back to normal service. Let me go shut the shades. I'll be right back. I'm really sorry. Be right back.
Did I miss anything?
What?
Did I miss anything? I wasn't here when.
He just went to go shut his blinds.
Okay.
Okay, guys, sorry about that. So if we have, so normally what we'd like is an amplifier with high input resistance. Because if you just think about this equation, so if you think of this as the sense input, so V sense is R amp over R source plus R amp times whatever this is, V source. So the higher this value is, you basically, if you're much higher than this R source, then basically these two cancel each other. I mean, basically this becomes much bigger than this, and then you get this over that, and you get basically one here essentially. And then the same thing with your output resistance. Whatever you're driving tends to have a resistive component. It's not 100% always all the time, but a lot of times it has a resistive component. And so at this point also becomes, we call this V out, say. V out is also an attenuated version of, let's call this V amp. So almost always, you want your amp to have high input resistance and low output resistance. And the reason I'm saying almost always is because, there's some environments like, not in the sense of microphone, but let's say, like some old video systems, etc. They had, they have I think audio has it too. They have a certain specific impedance connectors. So your input impedance, output impedance have to be exactly a certain number to avoid distortion. But those are very rare cases in my experience. So most of the time you want this to be true. Like 99% of the time is you want your amp input to have a high resistance and a low output resistance for your amp. Now, so we have three major configurations of amplifier inputs and outputs that's worth remembering because they come up over and over again. So the first one is a common emitter type of configuration. So essentially you're looking at your R in, so looking into the bass with the emitter grounded. This Rn is equal to R sub pi. By the way, let me say a couple other things about impedance before we do that. I think the main thing I'd like to say is this input output resistance is in the small signal domain. So that means that you basically, to figure out your resistances, what you do is you figure out what your bias points are, and then you calculate your input and output resistance. And sort of the lecture from last Tuesday talked about how you would do that, how you set up your network to do that. So anyway, so in this small signal mode, the input resistance of a bass with the emitter grounded is R sub pi. And R sub pi is just beta over G sub m. And G sub m is I sub c over Vt. So R sub pi ends up being beta Vt over I sub c. Okay, so to get so now here comes some trade-offs. So this is your equation for your input resistance. So generally, going through the base of a transistor gives you the highest resistance configuration. So you could go in through the collector, you could go into the emitter. So far, we've only really talked about the base being in the input, and that's good because it has a high input resistance. And it's what do I mean by high? It's typically something like this. You might have several kilo ohms input impedance. Depends on depends on the exact value of R sub pi, and the exact value of R sub pi depends on your beta and depends on your I sub c. So what you want to get is you want to have a transistor you want to have with high beta. Okay, it's always seems like it's almost always desirable, and you want to have low I sub c for high resistance. Okay, now, but here's a trade-off, because if you remember, the gain is minus GM R sub c, whatever your load resistance. Let's say you have a load resistance here, and GM is I sub c over Vt R sub c. So as you try to reduce your, sorry, as you try to increase your input resistance, you're going to have, you would try to reduce the collector current, but that tends to reduce your gain. So there's a trade-off there, and you got to figure out what gives you the optimal signal transfer from the input to the output. So you got to do, basically you got to make your input resistance high enough that it doesn't overly attenuate the input, but you don't want to make it, you know, making it high basically has the, you got to reduce I sub C, and that will reduce your gain. So there's a trade-off there. Okay, but so anyway, that's the first type of stage. The second thing which is good to remember, is if you're looking at your collector output with the base and emitter grounded, if you're looking down here, this output resistance is just R sub O, which is the early effect resistance. And this was V sub A over I sub C. Okay, so this one, again, you want to have, well, depends on what you want to have here, but that's anyway, a good thing to remember. So this is basically your early voltage. So if you remember, if you have a, let's see, a VCE over I sub C curve, the flatter this curve is, so this curve versus this curve, you'll be able to get a higher output gain out of something like this than you would out of this, and then have a higher output resistance. Okay.
Professor?
Yeah.
I was looking down in writing. Which one did you say you would get the higher gain out of?
You would get the higher gain out of something that has a higher V sub A. So this would have, this has a high V sub A. This is have a relatively lower V sub A. So you would get a higher gain out of this. If you look at it, if you look at a spec sheet for a bipolar amp. But you also see the V sub A values. Does that answer your question, Darren?
Yeah, it does. Thank you.
And then the next one too worth remembering is what's called an emitter follower. So basically looking into an emitter with the base grounded. This output resistance is going to be 1 over G sub M approximately. So this is a really good stage if you want low output impedance. Okay, because you can basically, you can increase the current. So again, G sub, I have to always write this, G sub M is IC over VT is VT over I sub C. Okay, the higher you make the current of this guy, the lower the output resistance. So this is really good for driving as an output stage. Okay, so you have to remember these three, or it's good to remember these three. It's in the slides, so I'm just repeating these slides here, this slide here. And those are the most common, I think. So easy enough to remember. Okay, so that's the stuff about impedance. Just as a quick review. The second thing is we were talking about biasing of bipolar transistors. Again, what you want to do is if your bias point is in a bad spot, either you are having no gain, zero gain. I think we saw an example of that in our recorded lectures, or you're in a situation where you have like a tremendous amount of current, or you're just simply shorted to a supply. And so you want this sweet spot of biasing. And for a bipolar transistor input, you want it to be the base emitter voltage to be in the 650 to 850 millivolts. And you, of course, you want the bipolar transistor to be in forward active mode. So somehow you have to create a bias circuit to achieve that. In the previous chapter, we just used a, like throwing a battery or voltage source around, but that's not really a practical bias circuit. You actually, in real life, you actually have to design a bias circuit that's inexpensive, it's physically small, and it's robust to variations in device parameters. So that's variations in manufacturing and variations in temperature, voltage, etc. So, I think where we stopped there was we had this really simple bias circuit, and it like barely worked. But we also saw how given a small change in a parameter like beta, so beta is one of those parameters that has a tendency to be always high, but it changes. So you're not going to see usually you're not going to see a beta of like 5 or 10 or even 20 in an NPN device. Usually going to be right around 100 or more, but it might have a plus minus 10%, plus minus 20% around that value. And you want to make sure that you can live with the variation that the manufacturer is giving you. Because there's usually a cost that goes into that, and usually you have a sort of a bill of materials limitation. You have a limitation of economics. You got to build your circuit for a certain price. So you got to make sure your circuit is robust to that. So the main variations, I think, for bipolar transistor, again, I always worry about beta and I sub S. So beta and I sub S, keep an eye on manufacturer spec and variations. So they'll tell you how that'll vary as you get this part. Does not guarantee that, if they say the nominal value of beta is 100, every part you get is 100. Anyway, that's where we stopped. Any questions up to that point? And if not, I think so that's where we stopped. So now we're going to start talking about a better device, okay, a better biasing circuit or improved biasing circuit. It's still, as you'll see, it still has some problems, but it's improved. So what's the idea behind this? The previous circuit was basically missing this. So let me cross it out for a second. And basically what it was relying on is I sub B being a certain value. And so you would get, this voltage V sub X would be VCC minus I sub B R1. So that's how this point V sub X would get set. And you'd have a certain current flowing through this guy, because this is a certain voltage. This will give you the VBE, and it'll give you the I sub C, etc. Now the problem was that you can't really rely on an exact value of I sub B. This showed up with variations in beta, but really that's the problem, is you're relying on this I sub B, this resistor you're picking. In a typical lab scenario, this might be the best you could do with this as plus minus 1%, which is pretty good. But the I sub B, because you might have big variations in beta, you don't really know for sure. So an improvement to this is to stick another resistor here. And the idea here is you can pick the values of R1 and R2, so that the current through IR1, so I'm going to put IR1, IR2. So in this circuit, if the current through IR1 is approximate current, the same as current to IR2, and these are bigger than I sub B, let's say they're a factor of 10 or 20, whatever, higher than I sub B, you can kind of ignore I sub B, and this voltage ends up being, so V at X ends up being a resistive divider of VCC. So again, if this holds, and we'll see after we do an example what happens if it doesn't hold, or if you want to get a more exact value. So if this holds, we can just sort of ignore this I sub B and say, okay, by picking the right R1 and R2, we're picking V sub X. And the exact value of I sub B doesn't matter. The exact value doesn't matter. All that matters is it's small enough that we can kind of ignore it because of these R1 and R2 values. And the way to do that is you pick R1 and R2 small enough so the currents through them are bigger than the I sub B value. Okay, so basically you end up with this voltage, V sub X, being that. And then I sub C is I sub S exponential of VBE over VT. Because this point's grounded, this guy V sub X is VBE, and we plug that in and get this expression for I sub C. Okay. So this is, if the base current is small, this ends up being relatively independent of beta. So let's do a quick example, see what this looks like. Okay, so let's say, let's see, so this is example 5.8 from the book, and we have VCC is 2.5 volts. We got our R sub C, we got our bipolar transistor. So this is our amplifier, and we're gonna put in our biasing circuit. So R1, R2, and the value for R1 is 17 kilo ohms, and R2 is 8 kilo ohms. And R sub C is 5 k ohms. They gave us I sub S as 10 to the minus 17 amps, and beta is equal to 100. Okay, so to begin with, assume I sub B is negligible. Negligible, I don't know, I probably misspelled that, compared to IR1 and IR2. So why don't you guys give a shot at figuring this out? Like what, so basically what I want to do is you want to calculate I sub C and I sub B. And two, we want to confirm that I sub B is negligible compared to IR1, IR2. Okay, so the procedure is, first you assume there is no current here. You figure out this voltage here. Use that as VBE. And then from there you calculate I sub C. And then from I sub C, you calculate back I sub B, and you've confirmed that it's smaller than the current flowing through these resistors. So why don't you guys give that a shot? Okay, guys, which brave soul will volunteer to help me out? No brave souls out there. Very wise. Never volunteer for anything. It's very important. So I'm gonna have to pick Joanna. Have I picked on you before? No? Come on, Joanna. Unmute yourself and join me. I have? Huh. I think it's because my wife's name is Joanna, so I tend to pick up on you. So okay, Joanna, I'm gonna trust that I did pick on you. How about Austin? Austin. Wait, what happened? Austin dropped out. Wow, this is scary. Did Austin bail on me? He did. Michael, you're next. Michael Guillermo. Sorry.
Hello?
Hey, Michael?
Yeah.
Okay, awesome. So can you help me out?
Yeah. So when we have to first find the V sub x,
Yeah.
and we just have to use the voltage divider rule.
Mm-hmm.
So it would just be R2 over R plus R1 plus R plus 2 times the collector voltage, or the VCC.
VCC, yep, you got it. So that's 17K ohm over 8K ohm plus 17K ohm. Did I get that right? Nope, I got it wrong. Sorry. It is 8K ohm times 25.5 volts. And that, did you get a number for that?
Yeah, I got 0.8.
Okay, great. Okay, so what's next?
And then since V sub x is VBE, we could plug that into the IC equation.
Okay,
Then, so it's IC is equal to I sub x, IS exponential VBE over VT, or
Mhm.
VX over VT.
okay. So that's 10 to the minus 17 amps, exponential of 0.8 over 26 millivolts. Did you get a number for that?
Yeah, I got 0.00023 amps.
0.0023 amps. Is that
Or
what you
one
got?
more zero.
One more zero, great.
Yeah.
Okay, that looks right. And then I sub B,
And then you just divide that by beta, or by 100.
yep. So I'm gonna put it in my sort of scientific notation, 2.31 microamp. So this would be also the same as 231 microamps. Okay, looks good. That's what I have. So then we need to confirm that I sub B is indeed negligible. So you got this one. How would you do this one?
I haven't gotten that far yet.
Okay, so it's actually all you do is you would sort of say, okay, if I sub B was negligible, I'd have a certain current flowing through these two. And you just have to calculate that and make sure it's higher than this guy. So let's try doing it. So it's basically IR1. Let's say if I sub B was negligible, then IR1 would be equal to IR2. It would be 2.5 volts over 17 k ohm plus 8 k ohm. So that's 2.5 volts over 25 k ohm. And that's blah, 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 blah. What do I have it? I've written down here. So it's 100 microamps. So we're comparing, 100 microamps flowing through these guys compared to 2 microamps flowing in here. So if you look at the ratio, so say IR1, IR2 over I sub B, the ratio is like 43x. So it's much, much higher than I sub B. So it's a legit approximation to ignore I sub B.
Okay.
Cool. Thanks, Michael.
Yeah, no problem.
Okay, great. So that's an example of, so now we have something that's just dependent on, again, it doesn't matter the exact in this case. Let's say I sub B instead of 2.31 was 4 microamp or 5 microamp, or it was 1 microamp or it was 7 microamps. It doesn't really matter because all we need to do is for it to be negligible compared to this current. Then, this point is, we're pretty good at this point. So you're not really looking for an exact value of our I sub B as long as it's much smaller than these two. And the way you make sure it's much smaller than the current going through these two is keep these values relatively small. Okay, you have a choice about picking these values. And what's important is the ratio of these two resistors. So it seems like a good approximation. I mean, it seems like a good methodology, I should say approximation. By picking the right value resistors, you can just make sure this current is much higher than I sub B. But you have potentially two problems or two trade-offs, okay, with making these smaller and smaller. The first one is this current through here adds to your power consumption. So you have a certain current I sub C, okay, which is the current you're throwing at your amp. That's 231 microamps. So the power consumption of the amp it's VCC times IC, and that's 2.5 volts times 231 microamps, okay, whatever that is, okay? And the power consumption of your bias is VCC times IR1 times, to make IR1 much higher than I sub B, we made it a relatively high value. So that's 100 microamps. So notice, because this power consumption for both is basically you take 2.5 volts multiplied by this current. So means that to create the bias, the power consumption of just this part, just to create the bias is almost half the power consumption of the amp, because the current is about half, and it's a little less than half. But it's a significant part of the amp power consumption. And like power consumption is always something that is you want to reduce. There's never a point where your customers, management, the rest of the people working on the project aren't going to care about power consumption. So this will be seen as pretty somewhat wasteful, okay, because you're just the biasing circuit is like a support circuit for the amp. That's very important, but it's still a support circuit, so you don't want to use too much power, and this is using a significant amount of power. So that's the first issue. The second issue you might have to worry about is that you'll have a source, your input, so we call it VN, is going to be driving this node. So we said the resistance of the amp. So this resistance is R sub pi. Okay, so that's cool. That's a resistance that we're going to try to maximize. But these resistors will also attenuate our source. They all look like resistive dividers with this input. So if you made this too low, you're going to attenuate the input. So not only will you have R sub pi to attenuate the input, but these will also start attenuating the input. And the question is, hey, is that significant or not? So you'll be under pressure to increase the value of these resistors, and it's possible that you may not be able to get away with making them too low. So there may be a case where you use this technique and I sub b is significant. So let's say if that happens, we need to come up with a methodology for seeing, calculating that bias. So let's say we have the same bias circuit, and now this current is relatively significant. So we need to come up with a methodology to analyze what happens. Okay, so we do it by coming up with an equivalent Thevenin circuit for this guy and using it to analyze what V sub x is. Okay, so the Thevenin circuit, we have successfully avoided, I think, looking at Thevenin circuits so far, but no more. So the way it works is a Thevenin circuit or a Thevenin equivalent looks like it has a voltage source and a series resistance. Okay, so the voltage source, so the Thevenin voltage of this guy, so it looks like basically this guy goes to, I'm just sort of redrawing this guy. I could just point it out here, but it's all here. Okay, might as well just point it out here. So basically we want to come up with a Thevenin equivalent of this. And what that looks like is you have a voltage, instead of having the voltage source VCC and these two resistors, you're going from this parallel configuration to a series configuration. So it looks like instead of VCC, you have your Thevenin equivalent voltage, which is this, which is VCC times this resistive divider, R2 over R1 plus R2. Okay, so that's the Thevenin equivalent voltage source here. And then a Thevenin series resistance, which looks like the voltage divider version of R2 and R1. Okay, so that is what looks like its input here. And then by calculating, by having I sub b, you don't calculate I sub b, by actually measuring I sub b or figuring it out, you can figure out how much voltage drop you have across the Thevenin resistance and how much that reduces the V Thevenin. Okay, another way to say it is you transform this thing into its Thevenin equivalent. Okay, so now you have this Thevenin equivalent, and you want to find V sub x. You want to find out what this VBE is. To find out that VBE, you use the Thevenin equivalent voltage, subtract I sub b times R Thevenin to figure out VBE from it, to get I sub c, and then from there you get I sub b, etc. We got to go through a kind of a iterative procedure. So let's do another example with this. Any questions about that? I know we haven't looked at Thevenin equivalent circuits, so you guys might be going, oh no. Any questions? Okay, so let me come on, where's our example? Okay, so let me grab this guy, so I'm being lazy. erase this stuff. Okay, so just as a reminder, we said if these resistors are low enough, we can get this current is much higher than I sub B, so we can ignore I sub B. Now, let's say because we're worried about power consumption and input resistance, etc., we make these resistors a factor of 10 higher. So instead of 17 kilo ohms, I say I'm going to make this 170 kilo ohms. And instead of 8 kilo ohms, I make this 80 kilo ohms. Okay, and I'm going to keep this as R sub C is 5K, and I want to come up with the same thing. So let's say we have the same I sub S. Let's see. So our I sub S is 10 to the minus 17 amps, and our beta is 100. And so we want to calculate I sub C and I sub B into, well, just calculate those two, I guess. It's an important thing. Anything else you want to do here? Let's see. Nope, just do that. Okay, guys, so the procedure is so A is come up with Thevenin equivalent for this VCC R1, R2 circuit. So this guy. So that's the first thing you got to do. B. So you have to, now this is the iterative procedure, is you have to assume a a starting value for VBE. And C, then you calculate, from there you calculate I sub B, I sub C, D, confirm VBE, and repeat to converge to a value. So why don't you guys give that a try, and we'll solve it together. Oops. Okay, guys. Let's see. I'm gonna try Austin again. Austin,
Yeah. Hello.
you disappeared last time.
I accidentally left. I had a keybind on my keyboard. I accidentally clicked it.
That's what I figured had happened. Or you do you want to take a shot at helping me figure this
Yeah.
out?
Yeah, I'll try.
Okay, let's do it. Alrighty, so let's do the Thevenin equivalent. So basically what that circuit will look like is so it's going to look like this: V Thevenin with a R Thevenin, then basically R Q1 R sub C. Okay, so what's V Thevenin look like?
Is it R2 divided by R1 plus R2 times VCC?
Yep. So let's see what value. Did you get a value for that?
Yeah, I got 0.8 volts.
0.8 volts. Okay, great. And then our R Thevenin.
R Thevenin is R1 in parallel with R2, right?
R1 over R1 plus R2.
R1 times R2 divided by R1 plus R2.
Like that.
Yeah.
Okay. And what do you get for that?
54.4 kilo ohms.
Yep. Okay, great. So we got those two values. So what did you assume? So next thing we got to do is we got to assume a starting point for VBE. What'd you assume for that?
Around like 700 millivolts or 750. I don't know. I haven't tried it.
Okay, let's try. I had assumed a smaller number. Okay, let's assume 750. That's a good guess. So let's see. So if VBE is, so our first assumption is VBE is 750 millivolts. So we got to figure out I sub B now.
Is it V Thevenin minus VBE divided by R Thevenin?
Yep, exactly. V Thevenin minus VBE over R Thevenin. And so that's 0.8 minus 750 millivolts over 50.4.4 kilo ohms. So that ends up being, what did I get for that? I got 0.919 microamps. Okay. And then what's I sub C?
I sub C is beta times IB, right?
Yep. So it's 100 times 0.919 microamps. And that ends up being 91.1 microamps. And then now we got to get VBE based on this. So that's VT natural log of I sub C over I sub S is equal to 26 millivolts natural log of 91.9 microamps over 1 times 10 to the minus 17 amps. I get 0.776 from that. And then, so what we do from there is we plug this back into here and get a new I sub B. The second version I got was 0.441 microamps. Got an I sub C of 44.1 microamps. And then I think I ended up with 766 millivolts etc. So you keep iterating, and then you basically converge to I sub C, I sub B. Okay, thanks, Austin.
Yeah, no problem.
So, by the way, guys, I've been thinking about, so we've done a few different problems with this iterative procedure for estimating VBE and then coming up with I sub C and using that to refresh our value of VBE, etc. And yeah, I noticed sometimes when I use the exponent, don't ask me why, I still haven't got my head around this. I don't know if it's like a numerical error or what, but if I use I sub C as I sub S exponential of VBE over VT, if I iterate like that versus something that's exactly the same. I mean, it's exactly the same, it's just a different version like this. If my iterations are in this form, they tend to like vary quite a bit when I'm like numerically calculating it. Again, I don't know if this is, just plugging stuff into your calculator and, it's because it's an exponential, a small number varies stuff, but this is just my experience, that I had much more luck when I used the natural log time form of, figuring out I sub C, then calculating VBE with this natural log function. I don't know why. It should be, to me, it should be exactly the equivalent. I don't know if you guys have noticed this yourselves or not, but it seems like sometimes this thing has a tendency to go like out of whack. Like instead of converging, it's like the same setup. Seems like sometimes instead of converging, it starts diverging. I'm not sure why. So anyway, just a tip that I found to be useful is to use the natural log form when you're doing this sort of exponential, or if you're doing this iterative procedure. Okay, so so this looks like a legit some methodology for biasing. Long story short is we have this approach that either there's a value for I sub B that we use a more complicated analysis technique, or if we're lucky, we can use a higher current through R1 and R2 and ignore this thing. Seems like this is kind of working, okay, as an approach. So this is almost there as a biasing technique, but it's still not really something that you can use in production. The reason is you basically end up with a voltage here. And although that voltage, you can count on it depending on the variation of these resistors, still there is some variation in those resistors. So let's look at the case where you can neglect I sub B. The voltage here is basically all that voltage is set by is the ratio of these resistors, R2 over R1 plus R2. Okay, but in a real scenario, you might get easily like 1% variation in those resistors. And you might, if you're using cheaper resistors, which sometimes you have to for budget reasons, you might get even more variations than that. And because this emitter is grounded, whatever variation you have, so whatever variation you end up in V sub x gets put into an exponential relationship with I sub C. So if you have, in this case, I sub C is I sub x exponential of, let's say V sub x plus whatever variations you have on those resistor values. Let's say it gives you a delta V sub x over VT. And so this exponential term tends to amplify those variations. So if you have a 1%, 2% variation in your resistance, it tends to get amplified and gets even higher in your value of I sub C. So there is, to solve that issue, there is yet the next approach for sort of a more robust approach to doing biasing, and that's using emitter degeneration, okay, which is this circuit. So it's taken, this part is exactly the same as before. This part is exactly the same as before. The big difference is we've put in a resistor at the emitter. So this not only, this is called emitter degeneration. I'm not sure why, but that's the name of this approach. You are sticking a resistor in the emitter. Again, not sure what's called emitter degeneration, but this has a bunch of, as you'll see, and we're going to talk about the next thing after biasing. We're going to talk about the common emitter stage in more detail. So we're going to go back just to the amp stage after we got the biasing. And you'll see that this has some other really interesting effects in terms of controlling our gain, etc. The upshot is by putting a resistor here, we tend to reduce the gain of this stage, which just seems like something you don't want to do, but you reduce the gain of the stage, but you make it quite a bit more robust. So you make the gain much more repeatable, and much less sensitive to variations. Okay, so let's see. Let's see what I want to talk about this. So okay, so in this case, just trying to think of like what's the best way to think about this. I think the best way to think about this is when you're doing this, so just sort of try to get your head around this. What we've done before is grounded this point. So I sub E was really just I sub C plus I sub B. But here what we're doing is we're putting, so let's say this is V sub X, right? This point, the emitter voltage is V sub X, V sub X minus VBE. Okay, everybody see that? So this is V sub X, there's a VBE voltage, and so this is V sub X minus VBE. And the emitter current is just this voltage divided by the R sub E. And that's approximately equal to the collector current. So I don't know how, like, you guys want to think about this. What I think about is this tends to kind of linearize this dependence of I sub C on VBE. It makes it more kind of a linear dependence on this variation VBE and less of an exponential dependence. Okay, I don't know if that makes sense or not. But basically, one way, I mean, I think one way to think about it is this resistor. So you have this voltage across this resistor. One way to look at it is that thing is like sort of absorbing or linearizing the variations you have in VBE. Okay, so let's do a, what do I want to say? I think that's pretty much it. Let's do an example. Let's do yet another example here. Oops. Rounds. With I sub s is equal to 5 times 10 to the minus 17 amps. Okay, so we want to figure out three things. One of them is the bias current. So I sub C, I sub E, I sub B, etc. By the way, one thing is to make the analysis easier. Notice we've got these resistor values small enough that we can neglect I sub B. We went back down to 16 k ohm and 9 k ohm, and we know that tends to be, and we have to verify that it is negligible, but so B, verify Q1 is in active mode. And C, you got to figure out, figure out change in I sub C with 1% change in R2. Okay, so we're kind of don't have much time, so I'm just going to do this. You guys try to, hopefully you'll try it, after the class. But anyway, so first thing we do is figure out V sub X. So I'm not going to go through the Thevenin procedure because, again, we set up the R1 and R2 so that we wouldn't have to for this example. So that make this current high enough, much higher than I sub B, and we'll see, hopefully we'll see that that's the case. If this wasn't the case, then we just do the Thevenin equivalent. So it wouldn't really be that different. But just to make things faster, we did it that way. So V sub X is just R2 over R1 plus R2 times VCC. So it's 9 k ohm over 16 k ohm plus 9 k ohm times 2.5 volts. And it's equal to 0.9 volts. So now I go through the same procedure. I assume a certain VBE, and so I assumed VBE of 800 millivolts. So this voltage, let's call this V sub P. V sub P is V sub X minus VBE. So it's 0.9 volts minus 0.8 volts. So it's equal to 100 millivolts. So I sub E is 100 millivolts over 100. So that is equal to 1 milliamp. And that's approximately equal to I sub C. Any question about what I just did there? Or how we ended up with that I sub E value? Okay, so now I gotta iterate. So you got to use this I sub C value to come up with VBE. So VBE is V sub T, natural log of I sub C over I sub S. So it's equal to 26 millivolts, natural log of 1 milliamp over 5 times 10 to the minus 17. And that gives me 0.796 volts. Okay, which is close to this. If you want, you could do, we can do a couple more iterations, but this is close enough here. And so, so I sub C is basically 1 milliamp. I sub B is 1 milliamp over 100, so it's equal to 10 microamps. So IR1 is 2.5 volts over 25 kilo ohms. So this is 100 microamps. So we assumed this was high enough. This was higher than this. It is by a factor of 10. So it was a good approximation to ignore. So okay to ignore I sub B compared to IR1, IR2. So that initial approximation was okay. So this is part A. We figured that out. B, we wanted to verify that Q1 is in active mode, which is something you always want to do once you're done with your biasing estimations. So B, we've got V at collector, call it V sub C. Let me call it V sub Y, so it doesn't get confused with VCC, V of Y. So V at Y is VCC minus I sub C, R sub C. So it's equal to 2.5 volts minus 1 milliamp times 1 k ohm is equal to 1.5 volts. So we had V sub X is 0.9 volts here. And this V sub Y is 1.9 volts. So we can see that, yes, we are inactive. We are, yes, we are V. And then C, let's see. Figure out a change in I sub C with 1% change in R2. Okay, so maybe we can think about that. So if, let's say, R2 is 1% higher than expected, or nominal value. So V sub X would be 9K times 1.01 over 9K times 1.01 plus 16K ohm. That's equal to 0.906 volts. So this V sub X goes from 0.9 to 0.906. Okay, which is So this is a 6 millivolt change. And let's assume that 6 millivolts drops entirely across R sub E. The reason I'm saying that is because that 6 millivolt change, some of it, a slight amount, may, your VBE might change by a small amount. So we're not gonna, because we're just talking about some small variations here. I'm not gonna worry about that for the time being, but let's say all of it goes across R sub E. So delta I sub E is 6 millivolts over 100 ohms. So that's equal to 60 microamps. And again, that's delta I sub C. So change in I sub C is 60 microamp over 1 milliamp, which is around 6%. Okay, so we kind of controlled the change in I sub C with the value of resistance variations by using this emitter degeneration technique. Okay, guys, any questions? No? Okay, guys, well, that's it for today. So talk to you guys on Thursday. Also, just a note, also put up a set of solutions to set of homework problems on Blackboard for you guys. All right, take care. Bye.
Thanks, Professor. Take care.
Thanks, Prof.